welcome to complex analysis. This is going to be the first session on a series of lectures on what I call Cauchy theory. And this session and perhaps the next one will be to prove Cauchy Goursat Theorem. What does it say? Remember, we said if I want to prove a continuous function as a primitive on a connected open set, integral of f over any closed path must be 0, right? So as a preliminary to that, what we are going to do today, suppose I have an open set and I have a triangle. Remember, triangle for us is a solid triangle. Okay, the interior. It's not only the boundary which you see in high school geometry. Okay, so the solid triangle should be contained in U. Then let us take a holomorphic function on U and integrate it only the boundary of the triangle, then it will be 0. Okay, this is what we want to prove. This is a very beautiful analysis, and till Goursat proved it, many times one assumed holomorphic function should be continuously differentiable on an open set. This is the first time he removed continuity is not needed. Okay, let us go through the proof. It will be very interesting. So there are certain preliminaries which let me see whether I have shared. Yeah. So there are certain preliminaries which you have to look at. So okay, suppose A, B, C are complex numbers. Okay, then what do I mean by a triangle ABC? Okay, that means this is okay. This is set of all complex numbers of the form, so that Z is of the form T1A plus T2B plus T3C, where T1, T2, T3 are greater than or equal to 0 and T1 plus T2 plus T3 equal to 1. Let's try to understand this. Okay, I'm not okay. A, B, C need not be this is need not be non-collinear. See, I'm not assuming, that means I'm not assuming A, B, C do not lie on a single line segment. I'm not assuming that they may lie. Okay, but let's try to understand. Suppose I fix a point A, right? For simplicity, let me assume as though they are not collinear. I have C and D, right? Then I know what is the line segment joining BC. Okay, this is by definition 1 minus T times B plus T times C, where 0 less than or equal to T less than or equal to 1, right? Now let's look at all A and take all line segment joining this. So let us start with a Z here. Then let's look at all line segment AZ. Okay, that is of what form? It is going to be 1 minus S times A plus S times Z, but that is same as, I mean, all points of this form. Okay, but this is nothing other than, so let us look at 1 minus S times A plus S times Z. This is 1 minus S times A plus S times 1 minus T times B, and then S times T times C. Is it clear? Now suppose I call it as T1 and T2 and T3. Is this clear? Each Tj is greater than or equal to 0, right? Now what is their sum? The sum is going to be 1 minus S plus S into 1 minus T plus ST. That is going to be 1 minus S plus S minus ST plus ST. That is going to be 1. Right? So what all we are doing is, what we traditionally know this, take this, okay, take all the line segments. So this is what, so notice that therefore for us triangle of ABC is so-called solid two-dimensional object, solid or two-dimensional area. Okay, it's not only the boundary. Okay, so understand this. So this is a, therefore this is a convex set. Okay, you can check it if you want. The picture actually shows that if I have a triangle of any kind, okay, take any 2 points, then line segment will always be there, right? But with this description, you should be able to check any triangle is a convex set. Number one. Number two, the boundary. This is what we denote by ABC. We denote by T of ABC. Okay, this consists of three line segments. What is this? This is the path. Let us look at that. A B. Okay, let me just write it BC plus CA. I am writing, instead of the usual star, I am just writing plus. Okay, for the time being, right? So what is this? This is AB, BC, and CA. Okay, so this is the path. So notice that this is a piecewise smooth, etc. Therefore, this is actually a path. This follow is a path. Okay, right. So let us state the theorem now. So what we do? So Cauchy Goursat theorem says the following. Let U and C be open. Assume A, B, C belong to U such that the triangle ABC is contained in U. Note again, please note that I am talking about the solid triangle should be contained in that. Let T equal to the boundary of ABC, which you denote by T of ABC. Okay, and let F be a holomorphic function. Then integral of F over gamma is 0. This is what the theorem says. Okay, so notice that the important thing is triangle. That is, for example, suppose I have a C star, right? Now let's look at this triangle. This we, okay, for example, let us say um, to square root I, and then this is minus 1 minus I and plus 1 I. Then let's look at this triangle. See, here T of square root 2I minus 1 minus I plus 1 minus I, this is contained in C star, but DI is not contained in C star, because the origin is going to play, okay, the troublemaker. Do you follow that? So for Cauchy Goursat theorem, what you should understand is the triangle, that is solid triangle, contained in that. Because the reason why I have to repeat is, from high school geometry, whenever we think of triangle, we think of only the boundary. You understand that? That is a specific reason I keep emphasizing in Cauchy Goursat theorem what is the hypothesis. Okay, so pause, review, proceed. Okay, before the theorem we need some preliminaries about this triangle. Notice that if T of ABC, okay, this is a path, right? This is a path, therefore call it simply T. So what is length of T? Okay, length of T, assuming this is non-collinear, Then length of this is length of all the line segments, right? Okay. Yeah. Okay. That's the first thing. And second thing, what is the diameter? Okay, of T. So let's look at this. ABC, right? So it's very clear, whatever line you take, okay, right? There are two points on the line segment joining them, and let us look at the measure. This is very clear. This is maximum of mod A minus B, mod B minus C, and mod C minus E. That is, okay, length of the maximum side. Okay, in particular, diameter is less than or equal to L of T. Okay, right. The third thing we need for this is the so-called Cantor intersection theorem. So before that, I will claim delta ABC is compact. Okay, why it's compact? Let us look at. With the description, you can see, if I look at this set, let us call it K equal to, okay, RST in R3, so that RST are greater than or equal to 0, R plus S plus T equal to 1. This means, this is, first notice that this is a subset of 0 1 cross 0 1 cross 0 1, right? Therefore K is bounded, right? And next, let us look at the map F from R3 to R. F of RST equal to R plus S plus T. Okay, this is continuous map, right? Therefore, when I restrict F to 0 1 cubed, this is 0 1 cubed, okay, right? Notice that this is closed and bounded, therefore this is compact, right? Are you following? So this map, okay, therefore F inverse of 1, this is closed set because F is continuous, intersected with 0 1 whole cubed, this is compact and hence it's closed, right? Therefore intersection of closed sets is closed, and this is closed subset of a compact set, okay, right? Therefore what we have, my K is F inverse of 1, which is a closed set, intersected 0 1 cubed, which is compact, and hence is obviously it's closed. Therefore K is a closed subset, and I also know it is bounded. Therefore Heine-Borel theorem says K is compact, okay, and hence now let's look at the map 5 from K to, if you want to see what is the map, RST going to, okay, fix ABC and see, look at the map, RA plus SB plus TC, okay, then this belongs to delta of ABC and this on to, okay. Therefore what I find is phi of K is delta of ABC. Therefore the triangle delta ABC is the continuous image of a compact set, therefore this is compact, okay. So pause, review, proceed. And fourth result I need is Cantor intersection theorem. right? What does it say? It says, suppose I have a metric space XD, or even a Hausdorff's topological space, or if you want metric space. Okay, this is what we are going to apply anyway. So if you want, you can assume it's a metric space. Okay, suppose I have Kn, okay, non-empty. This is an analog of nested interval theorem. Those who have followed my lectures on metric spaces, compactness, etc., you know that I have done this in both the places, in metric space as well as in general topology on compact spaces. Okay, so let me just quickly recall what it says. These are all non-empty compact sets. So remember, my space X is Hausdorff, therefore any compact set is closed. In case you don't know general topology, you know in any metric space, any compact set must be closed as well as bounded, right? Therefore these are closed. This is, it will be good to know they are closed sets, therefore hence closed, right? And like nested interval, let us also assume this is nested. Kn plus 1 is contained in Kn, right? For all n. Then what is that you should like to say? This Kn is not empty. Okay. In fact, if we further assume it's a metric space, I can assume extra. Suppose diameter of Kn goes to 0, then intersection of Kn is a singleton. In the metric space, I can say something much more. Okay. Right. Please assume this. I don't want to stop to prove this. Okay. Please, okay, look for this in my videos. Compact spaces. Okay. Right. So these are the facts you want to prove now. Use. Okay. Right. So let us start with the proof. Okay. All right. Notice that the first thing I want to say, so you start with a triangle ABC, which is contained in U, and where F is open, F is holomorphic from U to C. Okay. Assume this. Suppose ABC are collinear, then integral over T, let T equal to the triangle TABC, only the boundary of the triangle. Then it is 0 is obvious. Why? Suppose with a loss of generality, if they are collinear, okay, one point lies in between, so let me assume A lies between, okay, B belongs to the line segment AC. Okay, when it says lies between, what does it mean? I have A and C, and my B happens to be there. It may be other way around also, it doesn't matter, right? Now what was my triangle? My triangle definition was, the boundary was A to B plus B to C plus C to A. But remember, A to B, B to C is same as A to C and plus C to A, right? And these are reverse paths. Okay, these paths are reverse paths to each other, right? Therefore, integral f over T is going to be integral f over AC and plus integral of f over CA, and then more integral of f over AC minus integral of f over AC, which is 0. Yeah. Therefore, we will assume ABC are non-collinear. Okay. So pause. Review, proceed. Okay, next what we want to do. So the trick is, as I said, nested interval theorem. So if you have seen in real analysis proofs which uses nested interval theorem, what do? You take an interval and bisect it or trisect it and choose one interval, okay, for under certain conditions. Okay, again bisect it or trisect it. In that you choose one interval and so on. This is the way you do that. Do you understand that? How do you choose that subinterval of all the two or three subintervals at each time? Which one you to choose, that depends upon what you wanted to prove. Okay, this is why it's always good, okay, not to understand things only from the point of view of exams. Okay, please go through my article, or some of the things are nested interval theorem, where intermediate value theorem or boundedness of a continuous function and a closed and bounded interval, these are all proved using nested interval theorem. You will see the thing. Okay, so that kind of trick is very important in analysis, so please learn that. Okay, in case you have not learned, to use this as an occasion to go back and learn. You can read these proofs in my book on real analysis. Okay, so let's come back. So what is the trick? So I have, let me just draw a huge picture. I'll first explain the idea, then we'll go slow. It looks like a equilateral, but it need not be equilateral. Okay, now what do I do is, you look at the side opposite to A, choose the midpoint of BC, call it A1. And similarly look at the side opposite to B, call the midpoint of this as B1, and here C1. You understand? Now join these three. So I get a triangle, right? Now you see that I have four triangles, right? Therefore, what I want to do is, I want to say as triangle, yeah, the path integral f over t is equal to, I want to say path integral f over tj, j equal to 1 tn. I will explain what are tj. Okay, the first path is, let me use a different color scheme so that it will be easier. This one, this one, this one. Okay, therefore what is triangle t1? T1 is AC1. This is AC1. It's very important to think clearly. Plus C1B1 plus B1A, right? And what is T2? It's up to you which way you want to do. Okay, maybe it's T2. I should choose a different color. So let us write T2. T2. Let us say T2 equal to this, and this. Therefore, that is going to be C1B plus BA1 plus A1 C1, right? It will be good to have everything on a single page. It's unfortunate I started early. Okay, and now I want a T3. So let us look at T3. T3, let me use this and this and this. So T3 is going to be A1. See, let me not put comma so that it looks like 1 to me, so I'm just avoiding. C B1 plus B1 A1, right? Okay, now let's look at T4. I know, I'm sure all of you know what must be T4. What should be T4? That is this triangle, right? So this one I will write as, this is a different color. So let us, I hope I chose a different color. Therefore, it's going to be A1 B1 plus, okay, B1 C1 plus C1 A1. Where is my cursor? Yeah, again I should have that thing. C1 A1. If you have been following my path intervals carefully, you will already see something very interesting. Yeah. So let us look at. Okay. I will simply treat each other as integral. Are you happy with that? Suppose integral f for tj, I will simply write whatever that integral. That's it. I will write it. Okay. The sides of the thing, that is integral over this side, integral over this side, integral over this side. For simplicity, let me assume these things. Okay. Now let's add all these four. Right. Now let's look at what are the things you are cancelling. You can see c1, b1, c1. Okay, that is going to be, let us use a different color scheme. I don't know whether I have enough colors here. Good. Right. Okay, let us see a1 b1. Okay, a1 b1. Okay, that gets, okay, connected with this fellow, right? You see that a1, I have a1c there. I should have a1c, yeah, and b1 a1. Is that okay? Integral over this cancel with integral over that. Please understand what I am trying to say. I am looking at integral of f over tj, and that is over summation. But that is going to be, okay, integral each f over tj will be f over integral of f over some side. Okay, let us side j1 plus integral of f over side j2, second side, integral of f over side j3. Okay, what is a j1, j1, j2, j3? Like this, j1, j2, j3, which are line segments. Are you following? Now what I am claiming, something like this here is going to get cancelled with something else. Okay, please understand, do not get confused. Okay, for simplicity I am using it, otherwise I can use all these integrals, but it will be easier to look at this way. Right, now let's look at this flow. b1 c1 gets cancelled with c1 b1. Okay, b1 c1, where does it come? So I have b1 c1, this is red I believe. Okay, where does it come to? It comes to a1 c1, c1 b1, c1 b1. You follow that? They get cancelled. Right, now let's look at c1 a1. c1 a1 should get cancelled with this flow, that is, which starts from c1b onwards, that is c1b and ba1 and a1 c1. So a1 c1, that cancel with c1 a1. Right, therefore what I have now, so what I have is integral f4 tj happens to be integral f4. Okay, again I will not write. Okay, integral f over what are the intervals is what I am going to write. Now let's look at, so I have a c1, I have c1b somewhere. Yeah, where I have c1b, right? So connect these two things. So that is going to be AC, right? So that is going to be integral over AC plus next will be integral over, let's see, now BA1 and A1C should be there. Okay, BA1, where is BA1? Let us use something else. BA1 and A1C is here. So that gives me integral over BC. Integral over, I'm sorry, I should have said integral over AB. I wrote as AC, but it should be integral over AB. Go back just to make sure I am not goofing. Okay, AC1 plus C1B will be AB. And the next one is CB1. Yeah, where is CB1? Yeah, CB1. So let us use a different color again. CB1, and I should have something like B1A. B1A. Okay, that is integral. Okay, I'm sorry, that doesn't look nice. Integral CA. But that is integral of F4. You understand this? So we proved it. So pause, review, proceed. So in summary, what I have shown, I have a like this and connect it to the mid sides. Okay, then I have 4 triangles. I'll call it T1, T2, T3 and T4. Okay, then what we said is integral of f over summation Tj is same as integral of f over t. Okay, this is what we wanted to prove. Now what is that I wanted to show? I want to show integral of f over t is 0. So it's enough if I show integral of modulus of this interval is 0, right? So let us do. Therefore, modulus of integral f over t is modulus of this summation, but that's by triangle inequality less than or equal to modulus of integral f over tj, j equal to 1 to n, 1 to 4. Do you agree with that? Okay. Now let us look at, this is sum of 4 terms, right? So let us look at, I claim there exists at least one j. Okay, so that modulus of integral f over tj is greater than or equal to 1 by 4 times integral of, sorry, modulus of integral f over t. Why? Because if each one of them is less than or equal to, okay, if each one of them is strictly less than 1 by 4 times in modulus of integral f over t, then the sum will be strictly less than modulus of the integral f over t. That's a contradiction, because this fellow is actually less than or equal to. Are you following? If each one of them is less than, this will mean, okay, this is going to be less than 4 times 1 by 4 modulus of integral f over t. That is modulus of integral f over t. So that's a contradiction. You see that? Therefore, there is one C. Okay, pause, review, proceed. So now you see the pattern. We subdivided the triangle into 4 sub triangles, and we are going to choose one of them. You understand that? So call that as T1. So this, okay, call Tj as T1 and ignore the rest. Okay, now do not worry about T2, T3, T4. Okay, they are all ignored. If otherwise, I should say T11 plus T12 plus T13 and T14, and T1j is the correct triangle for which it happens. So I am removing all other 3. Okay, and call T1j as T1. Are you following? Okay, so I am going to use T2. You should not think of T2 as the earlier one which I did. That's why I am saying. Okay, my triangle T was written as T11, T12, T13 and T14, and we said integral f over t equal to summation over j equal to 1 to 4 integral of f over tj etc. T1j. Okay, so there is 1j, so that modulus of this fellow is greater than or equal to 1/4 of modulus of integral of f. Okay, over t. So that T1j is what I am going to call T1. Is that clear to you? Okay, make sure. Now what do you think I should do next? If I had understood Nestor-Rolle theorem argument, what will I do? Apply the same trick. T1, that is subdivide T1 into 4 triangles and carry out similar argument. Okay, keep this in mind. Okay, we will go slow. Before going further, let's look at what do I know about length of T1. Notice that I have this. Okay, It could be any one of them, right? But remember, using similarity of triangle, you will see each side is going to be half of this side is going to be half the length of this, and this side, okay, is going to be half the length of this, and this side is going to be half the length of this, right? Therefore, this is what we have is this is 2 to the power minus 1 of length of t, where t is our t of ABC. Yeah, right. And also the diameter of T1 is again half the diameter of T. That is again 2 power minus 1 diameter of T. Is that clear? And of course T1 is contained in, and okay, the triangle, okay, the triangle, call it A1 B1 C1, that is T1 equal to T of A1 B1 C1, whatever they are. Okay, this is contained in triangle ABC. Okay, and for the same reason this is compact. So now do you see how the Cantor intersection theorem is going to play a role? Just think about it. Okay, just go ahead with the proof, have some kind of an idea. Okay, this is how you develop intuition how to work with proof rather than line by line checking, right? Okay, now what do? I look at this triangle T of A1 B1 C1, and also what did we know? Also we found out this, also let us mark it. I have integral of f for T1 in modulus is less than or equal to 2 power minus 1, 2 power minus 2, that is 1 by 4. Okay, let me write 4 to the power minus 1 of integral mod f over T. Okay, yeah. So what I am saying is I have chosen T1 with the following properties. Length of T1 is 2 to the power length of T, and diameter of T1 is 2 inverse diameter of T, and 3 modulus of integral of f over T1 is greater than or equal to modulus of integral of f over T. Okay, and 0 delta of A1 B1 C1 is contained in delta of ABC. These are the 4 properties we have. Now apply the same logic. So what will I do? I'll take triangle T1, which is T of A1 B1 C1, and okay, find the midpoints of each of the 4 sides and do that. And then what will I have? I know there exists a T2. Okay, so that length of the interval of f over T2 is greater than or equal to 1 by 4 length the modulus of the integral of f over T1. Okay, but what is this? That means this is greater than or equal to 4 to the power minus 2. Maybe I will call this as I, where I equal to modulus of integral of f over T, so that I don't have to keep writing. Yeah, and what do I know about length of T2? Length of T2 will be half of the length of T1. That means 1/4, that is 2 to the power minus 2 of length of T. And similarly diameter. Right? And of course delta of A2 B2 C2 is contained in delta of A1 B1 C1. That in turn, let me call it simply as delta 2. Delta 1 is contained in delta ABC, that is delta. Okay, and the integral of f over T2 in modulus is greater than equal to 4 to the power minus 2 I. These are the 4 properties. Is that clear? Pause, review, proceed. So by induction we find, okay, nested sequence of triangles delta n such that 1 delta n plus 1 is contained in delta n for all n, right? 2, and if Tn equal to the boundary, the triangle, then length of Tn equal to half of length of Tn minus 1, therefore it's equal to 2 to the power minus 1 length of T, and 3, diameter of Tn equal to 2 to the power minus n diameter of T, and 4th, integral of f over Tn in modulus is greater than or equal to 4 to the power minus n times I. Okay, so just try to see whether you can write on your own now. Okay, pause the video, take a pen and paper, okay, right, and turn the other side and try to write down whether you can write down the induction hypothesis carefully. Right now, do you see that how we can apply Cantor intersection theorem? So these kns, these delta n's, okay, sequence of compact subsets which are nested sequence, and none of them is empty, right? Therefore intersection delta n is non-empty. In fact, it's a singleton. Call it Z0. Why it's a singleton? Because diameter of delta n goes to 0, right? Therefore, okay, now you see that this is the place where we are using the important thing in the hypothesis. We want the solid triangle should be contained in U, right? If the intersection, okay, now remember all these delta n's are contained in U itself, right? Therefore intersection delta n, which is Z0, okay, that must be a point of view. You understand? Just to try to imagine, suppose I have some such thing, this is my origin is left out, I may get some such triangle like this, okay. If I keep going, I may end up in 0. It may not be in the domain. It's intuitive, okay, just to show you how I need the hypothesis, okay. But if you are one of those guys who don't want to be okay, look at this kind of thing, just ignore, okay, right. Now therefore Z0 belongs to you. So what do I know about that? Now let's look at, so far I know we have not used the fact f is a continuous, say, holomorphic function. Now f from u to c is holomorphic. Therefore at Z0, if you give an epsilon positive, there exists a delta positive, so that whenever 0 less than mod h less than delta, or let us say mod z minus z0 less than delta, I know f of z minus f of z0 minus f dash of z0 into z minus z0, okay, in modulus is less than epsilon into mod z minus z0. Okay, this is the definition of differentiability. Remember that f of z minus f of z0, z minus z0 minus f dash of z0. Okay, this is less than epsilon for 0 less than mod z minus z0 less than delta. Therefore just multiply everything out, then you get this inequality. Okay, okay, have you understood? Okay, now we can so I can assume this delta is such that b z0 delta is completely contained in U. Choose delta such that this and this also holds. Okay, so I have u, I have z naught. Okay, I have, this is my b z naught delta, right? Now what do I know? Remember, all my delta n intuitively goes to z naught, right? Intuitively, but don't worry about such things. But what I want to say is, okay, now diameter of delta n, okay, goes to 0. That is, it is 2 to the power minus n diameter of delta. Is it okay? Sure. Right. Now notice that this goes to 0. Okay. Therefore, are you following? Therefore, if I start with any z n, okay, there exists a capital N, so that delta, for n greater than or equal to capital N, my delta n will be contained in b z naught delta. How many of you understand this? So what does it mean? If I start with the z in delta n, right? Let's look at, okay. Now z naught belongs to delta n for all n. Do you understand this? Yeah. Therefore, let us look at distance between z minus z naught. This is less than or equal to diameter of delta n. Yeah. So if I choose n such that diameter of delta n is less than delta, because that goes to 0, I can choose this. Therefore, diameter of delta n will be less than delta for all n greater than or equal to n. You understand that? Therefore, this will be less than delta. That means the n, okay, for all n greater than or equal to n, my delta n is contained in b z naught delta. So pause, review, proceed. Okay. Now let's look at this. So what I have now? So I wanted to show integral of, that is f over t modulus, that is I want to show it is 0. So if you give me any epsilon positive, if I show I is less than epsilon, okay, enough. Okay, I am through. For every epsilon, if I show this, I am true, right? So let epsilon be given. Choose delta, okay, as above. That is, it satisfies one as well as b z naught delta is contained in u. Okay. Now also choose n accordingly. Therefore, for n greater than or equal to n, my delta n is contained in b z naught of delta. So fix one such n. Right. Now let us look at. Therefore, for every z n, this Tn, see delta n itself is contained in this. Yeah. Therefore, Tn is the boundary. Therefore, z, for z in Tn, z also belong to this. Therefore, mod z minus z naught is less than delta. Therefore, what do I know? F of z minus f of z naught minus f dash of z naught into z minus z naught in modulus is less than epsilon into mod z minus z naught. Okay. Now that means I want to estimate integral of f for Tn. Tn, where n is n in greater than n is fixed. Okay. This one. So this one I know is less than or equal to. Now I want to use ML inequality. Right. First I claim that integral of f over Tn is, okay, integral of f of z minus f of z naught minus f dash of z naught into z minus z naught over Tn. This is just f. Okay. Why? See, by linearity, this integral of f for Tn minus integral of f z naught over t and minus integral f dash z naught into z minus z naught over t. Is that okay? Right. Now notice that this is a constant, t is a closed path, therefore any constant function has a primitive, namely f z naught into z. Okay, if I define g of z, g prime of z is f of z naught, right? Therefore this is 0. And similar reason, this also has a primitive, namely f dash z naught into z minus z naught squared by 2. Remember f dash z naught is fixed constant. Okay, therefore this is a primitive for this function. T is closed, therefore this integral is also 0. Therefore I got the integral. Do you understand that? Therefore, so what is the important observation we found? Integral f over Tn is integral of f minus f of z naught minus f dash of z naught into z minus z naught over Tn. Right? Now I wanted an estimate for this. Therefore, modulus of this integral. Now I want to use ML inequality. Okay, but I already know what f of z minus f of z naught minus f dash of z naught into z minus z naught. I want to estimate for all z in Tn, right? But this is I know is less than or equal to epsilon times mod z minus z naught, right? But where does z belong to? Z belong to Tn and z naught also belong to Tn. Therefore, this will be less than epsilon into diameter, less than or equal to epsilon into diameter of Tn. Do you understand the constant? Yeah. Therefore, by ML inequality, this fellow, okay, this fellow is less than or equal to epsilon into diameter of Tn into length of Tn. Have you understood? Okay, good. Now we are almost through. So what have you found? I have shown that integral of f over Tn in modulus is less than or equal to epsilon into diameter of Tn I know is less than or equal to 2 to the power minus n diameter of T, and other one is diameter of delta, length of delta, sorry, length of delta, right? Length of delta Tn is less than or equal to 2 to the power minus n length of T. Have you understood? Yeah. Okay. Right? But what do I know integral of f over Tn? How did I choose this? This I know is greater than or equal to 4 to the power minus n and into I. Yeah. Therefore, what I have is 4 to the power minus n into I is less than or equal to modulus of integral of Tn. That in turn is less than or equal to 2 to the power n minus 2 to the power n is constant. Therefore, 4 to the power minus n into diameter of T into length of T into epsilon. Okay, that means I is less than or equal to some constant c times epsilon, where constant is diameter of T into length of T, which is okay, which does not depend upon n or anything. Yeah. So what I have shown, therefore the epsilon is arbitrary, therefore this implies Ti is 0. So pause, review, proceed. So I hope you enjoyed the proof. Please go through that. Okay. And as I said, in case you have not seen nested interval theorem, how it is proved to prove some results about continuous functions. Okay. Two standard examples are intermediate value theorem and also boundedness theorem for real valued continuous function and compact intervals, closed and bounded intervals. Okay. You can look at it in my book or in my article. Okay. Use of nested interval theorem. Learn that well, because that argument is very important. That's exactly the argument we used here also. Okay, please go through that. I hope you enjoyed the proof. We will look at what are the consequences of this theorem in the next session. Take care, stay safe.